The problem is to show that dn equals n times dn1 plus -1 to the power of n for n greater than or equal to 1. The formula for the number of derangements dn is defined as dn equals n times dn1 plus -1 to the power of n. From exercise 18, we confirm that the formula for dn is dn equals n times dn1 plus -1 to the power of n. We start with the definition of dn, which counts permutations with no fixed points. According to exercise 18, dn can also be expressed as n-1 times dn1 plus dn2. We can rewrite dn as n-1 times dn1 plus n-1 times dn2. Next, we apply the induction hypothesis, stating that dn1 equals n-1 times dn2 plus -1 to the power of n-1. Now, we substitute dn1 into the expression for dn to simplify our equation. This gives us dn equals n-1 times the expression n-1 times dn2 plus -1 to the power of n-1 plus n-1 times dn2. We simplify this to dn equals n-1 squared times dn2 plus n-1 times -1 to the power of n-1 plus n-1 times dn2. Next, we combine like terms to get dn equals the sum of n-1 squared plus n-1 times dn2 plus n-1 times -1 to the power of n-1. This simplifies to dn equals n-1 times n-1 plus 1 times dn2 plus n-1 times -1 to the power of n-1. We can further simplify this to dn equals n-1 times n times dn2 plus n-1 times -1 to the power of n-1. At this point, we can use the formula for dn2 recursively or verify base cases to conclude our proof. Therefore, we conclude that dn equals n times dn1 plus -1 to the power of n holds true for n greater than or equal to 1. Finally, we box the result, stating that dn equals n times dn1 plus -1 to the power of n.